All right, I want to do an introduction to iterated integrals. I'm just going to do an example. And the most basic, definitely not the only example, but the most basic is to find the volume of an object. And I often use two metaphors, a house or a loaf of bread, and you'll see why. And I totally mix these metaphors at will. Sorry about that. Okay. And so what I want to do is I want to find the volume of the object. Let's call it a house for right now, where the floor plan is the rectangle 0, 2 cross 3, 4. Now what does that notation mean? We know what the interval notation means. What does this cross thing mean? It means a rectangle where the x's are in here and the y's are in here. So it's, in other words, it's the set of x and y such that x is between 0 and 2 and y is between 0 and 4. Okay, so let me go ahead and erase a little bit. So that's going to be the floor plan. I'm not going to draw the three-dimensional picture yet, and it turns out to be very important to draw the floor plan, and often it's really what all you need. But so that's going to be 0 to 2, and that's going to go 1, 2, 3, 4. Okay, so it's going to be this rectangle up here. Okay, now let's draw the three-dimensional picture. I'm going to tell you what the actual house is. Okay, it's going to be the floor is going to be just the xy plane, and that's going to be standard for a little while for us. We'll get more general in a little bit. And then the roof is going to be z equals 8 minus x minus y. Now that happens to be a plane as well, but in general it could be any kind of the graph of any surface. Z equals f of x, y. Okay, 8 minus x minus y, what does that look like? When x and y are 0, it's 8. It comes down here at 8 in the x direction and 8 in the y direction. Okay, and so that's going to be the plane, but it's not all of this plane that's really active as the roof. Remember, y is going to y is between 3 and 4, and x is between 0 and 2. It's that little rectangle here that's the floor. So we're just going to have to draw that bit of the plane. Well, we just can kind of go up here and slice out kind of this bit. Okay, so we have to have some sort of half-assed picture if we want to get an idea of what's going on with these things. But it doesn't have to be very good. Okay, notice what I did is I drew the floor plan, and then from each corner of the floor plan I tried to go up to approximately where the roof would be, and then I just kind of shaded in. Okay, so it's the volume of this little house. Okay, so in fact let me go ahead and make that a little bigger because I want to illustrate something. Okay, so I'm just gonna zoom in a bit. Actually, let me put it up a little bit because it's mostly in this quadrant. Okay, so I'm just going to zoom in. Here's that floor plan, and I'm going to maybe de-exaggerate a little bit. That's not very good. Okay, that's the right idea. Okay, so it's this region in here. Here's the roof, here's the floor, and here's the back corner. Okay, and how would I find the volume of this? Well, it's really the same idea as we had in BC Calculus, which is, and there's going to be other strategies, but the first strategy is just to do slices. That's the most basic strategy we had for volumes in that setting, and that was really doing Calc 3 and on the cheap, basically, but we're going to do it just a little bit more real here. So we can slice up this thing, and this is where the loaf of bread metaphor is useful. We can slice it up. Let's say we slice it up with slices that are parallel to the xz plane. We don't have to do it that way, but it's one way to do it. So we're going to take a slice. Let's say the bottom of the slice looks like this. Notice it's running in the floor plan. Here's the size of the slice. Here's the top. And so here's a slice of bread from this loaf. And so what we're going to do is we're going to take the volume is just going to be the sum. It's really an integral, because these slices are going to be infinitesimally thick, of the area of each slice. Well, let's see, what is that a function of? The variable that controls which slice we're talking about is, for this choice of slicing, it's the y variable. So it's going to be area as a function of y times the thickness, which is a little bit of change in y dy. That's exactly from BC. It's even from AB calculus. That's not new. What's new is that in AB calculus or BC calculus, we only did examples where we didn't have to use calculus to find the area of the slice. But you know what? We already know calculus. And so what we're going to do is we're going to be able to do any kind of situation where if we take this slice and we rotate it a little bit, it's going to be something with this kind of slanty top. This is the front face of the slice just pictured. That's an area problem. Hey, you know what? Let's see, what variable runs along here? It's x. Okay, oh, actually, you know what? I rotated it the wrong way. As x increases, this thing is slanting down, so it's actually slanting down like this. I really should have rotated it kind of like this, I guess. Okay. So as x, if I want to find the area of this slice as a function of y, I just want to figure out what are the equations of this top line for a particular y, but as a function of x, and find this area. So we're going to take an integral, an outer integral, to collate all these slices to produce a volume, but each of these guys is going to be an integral in itself. Okay, so again, I don't have a lot of room. I don't want to kill my good picture. Let's just go ahead and... Okay, so the volume is going to be the integral in dy. Now, what are the limits in y? Well, we just look at our floor plan. That's 3 to 4. Those are the applicable y's. Then, remember, I'll just put it right over here, this picture. For each slice, for a fixed value of y, that's a fixed slice, and I just need to describe the integral here. Well, that's exactly a standard problem, the area under a curve. That's going to be the integral from, now what are the x limits? That goes from 0 to 2. Of the height of this guy. But the height is exactly just the function. That's an integral in dx. And then I'm going to integrate dy. So notice the structure here. This inner integral, x is a dummy variable. It's the variable of integration. It gets discarded once we do the integral. But y is an honest-to-God variable because it talks about all the different slices. This is a bunch of different integration problems for the different slices depending on what y is. Then this thing becomes a function of y. Then that gets demoted to a dummy variable because then you collect all those slices together and you integrate. So you just evaluate these guys inside out. This is just an ordinary integral in x. Y is treated as a constant here because for each of these different slices, y is fixed. It's a fixed slice. Y is a constant. It's very much like partial integration. There's a deep connection between, partial derivatives, between partial derivatives and iterated integrals. So this is going to be 8x, because that's the variable, minus 1/2 x squared minus xy, because y is a constant, and then it's times x. And then that's going to be evaluated from, and I'm going to put x equals to really be careful. And like you don't usually put the x equals, you don't usually put the brackets, but we'll do that for right now. Okay. Equals, and let's see if I can squeeze it in. No, I can't. Well, let me see if I can be, yeah, give myself a little more room. Try to focus better. Okay, 3 to 4. Okay, so now it happens to be that when x equals 0, this all dies. Don't assume that's always going to happen, but here it does. So this is going to be 16 minus, and then 2 minus 2y dy. So in other words, it's the integral from 3 to 4 of 14 minus 2y dy. That is not hard. So what is this? Remember, the 14 minus 2y is the endpoint of this calculation, that I sliced it into all these slices perpendicular to the y-axis, parallel to the x-axis, and 14 minus 2y records as a function of which slice I'm on what the area of each slice is. And then area of slice times thickness of slice integrated from 3 to 4 gives me the actual volume. And let's finish that up. Try try not to erase that. Okay. And so that's going to be 14y minus y squared from 3 to 4, which is going to be 14 times 4 is 56 minus 16 minus 42 minus 9. And that's 40 minus 33. The whole thing is 7. Let's see if that's plausible. The whole thing was in this inside an 8 by 8 by 8 cube. Now that would be pretty big, but it's a very small portion of it. This area here was just a 2 by 1, so that had area equal 2. And so let's see. If this were a box, this would be a 3.5 by 2. Well, that seems reasonable. What that's saying is the average height we're claiming is 3.5. Makes sense. It's roughly halfway between 0 and 8. Okay. And that's a very important other use of these integrals, not just calculating volumes. The average value of a function of f on some rectangle R, what you do is you build a house with that function on the rectangle. That's the integral over R. So this is putting them right next to each other and just putting the symbol R. It just says integrate over whatever that rectangle is. And then you can put in the limits explicitly for the iterated integral of f of xy. And then there's a nice abbreviation. We'll talk about this in a little bit of a different way. Instead of putting what we had before was dx dy, well, that's really a little bit of area. Dx is a little bit of length, dy is length in another direction, and it's really a little bit of area. And we'll talk about more conceptually why that's true. You take that volume, so that's the volume of the house you've got, like this thing. And then what should be the average height? It should be, if you can replace that with a box that has just a flat top that gives you the same volume, then that flat top, that height of that guy, should be the average. Or in other words, what we're going to do is we're just going to divide by the area of the rectangle. So this is another really great use of iterated integral, partly because there's going to be a lot of things like, suppose like f was like the temperature of a hot plate. The integral, like the total temperature on the hot plate, that's not an obviously meaningful quantity. But the average temperature on the hot plate is very, very meaningful. And so often it's really this average quantity that's going to actually be a little bit more important. But they're very closely related. You just take the integral and you divide by how big a region you're integrating over.